for today's session.
Thank you very much, Chairman. Good afternoon, ladies and gentlemen. Today I am going to talk about my present research on the topic of microwave-assisted selective heating of WO emulsions and its application to microreactor for enzymatic reaction. My name is Mohammad Azizul Haq. I am a postdoctoral researcher here. So first of all, about the background, we know that about the emulsion, there are two kinds of emulsion. One is OW emulsion and another is WO emulsion. WO emulsion means water in oil emulsions, where the dispersion phase is water and where the dispersion phase can be heated under microwave heating. So if you see here the oil is continuous phase and the water is dispersion phase. When we make emulsion, so the water dispersed inside the oil phase. And under the microwave heating, microwave can heat it of the droplets of dispersion phase. So from the previous study, we see that they have shown that the dispersed phase temperature is around 20 degrees higher than that of continuous phase. But it is very difficult to measure the temperature of dispersion phase. So in other studies, we have seen that the fluorescence molecular thermometer can be used as a measuring tool of temperature. So we have used this fluorescent molecular thermometer to measure the temperature of the dispersion phase. As you know that what is the difference between the conventional heating and the microwave heating? We know that the conventional heating, the heat source is from outside and the heat is conducted from outside to inside and by conduction and the convection. But in case of microwave heating, we see the heat is generated inside the microdroplets of high dielectric loss substance. And we have also seen from the previous study that microwave can be used to activate the catalyst. And we have seen that from the conventional heating and the microwave heating can generate manifold of reaction rate. So we can say that the microwave can be used as a heating source, a heating system for catalyst. In the other studies, we have seen that in the gas-liquid interface, microwave can enhance the reaction rate. If we see that below the boiling temperature, there is no effect of microwave in activation energy and the reaction rate, but over the boiling point, it shows zero water kinetics. And we have seen about the ACS Catalyst journal that deep glucose or sugar can be converted to the deep fructose using enzyme or biocatalyst. And there are many enzymes currently used to catalyze the deep glucose to valuable products like glucose isomerase, invertase, alpha amylase, glucose oxidase, and cellulase, etc. Some are high temperature enzyme and some are low temperature enzyme. So we have set our objectives like analysis of microwave induced local temperature of WO emulsions using fluorescent molecular thermometer and use the dispersed phase as microreactor for enzymatic reaction. We have set three different experiments. That the first we have evaluated the microwave absorption characteristics of microwave heating behavior of emulsions, and then we will evaluate the local temperature using rhodamine B as a molecular thermometer. And finally, I will show the application of a microwave for a microreactor where enzyme is used. So the first experiment is microwave absorption characteristics and microwave heating characteristics of emulsion. As I said before that, we have two types of emulsion, OW emulsion and WO emulsion. So first we measure the complex dielectric constant measurements using the coaxial probe methods, and we have evaluated the WO emulsion and OW emulsion microwave heating characteristics using 2.45 gigahertz microwave heating device. And finally, we will simulate this experiment with using the console multiphysics. So here is the result from the measurement of dielectric constant of emulsion. As you see the left figure, that this is for the OW emulsion, and we have seen that the first result dielectric constant measurements are shown here. It shows that the tan delta with respect to the frequencies, and the higher the value of tan delta, that means that it is easier to be heated by microwaves. In the OW emulsion, there was no change in tangent del, even in the dispersed phase concentration was changed. In W emulsion, we see that from 1 to 6 gigahertz, the tan delta of the emulsion is higher than that of paraffin. If we see in the higher frequencies, we see the difference of liquid paraffin and the dispersed phase difference of tan delta. That means we can say that the red one is dispersed phase is 40% emulsion. That means the water percentage is 40 here, so it is heated up earlier than the paraffin. So we summarize the results of evaluation of microwave heating behavior of emulsions. We see from the OW emulsion, if we change the dispersion phase in OW emulsion, that means that the dispersion phase concentration decreased as the temperature increased. But in case of W emulsion, we see that the temperature increased as the dispersion phase concentration increased. That means it's indicating that the dispersion phase may be exothermic, and that this dispersion phase is absorbing the microwave and can be heated easily. So we found did the microwave heating characteristics by the simulation. We see that in OW emulsion, the center is the oil and outside is the water. This oil droplet, if you see the intensity of the heat is watt per meter cube, we see that the high temperature is around the circle. Inside is the oil droplet and outside is the water. And in case of W emulsion, we see that only the water droplet is heated up. So we can see that microwave can be heated selectively. And this is the time for the measurement of the temperature. So we have done the experiment using the molecular thermometer, fluorescence thermometer, local temperature evaluation using rhodomain B as a molecular thermometer, and we have used conventional heating system and the microwave heating system. And we have done in situ experiment inside the conventional heating device and the microwave heating device inside the fluorescence spectroscopy. So this is the results from this fluorescence spectral measurement. We have seen that from the conventional heating, if you heated up the substance, then the intensity is get down. So this is 20 degrees Celsius, so it is very visible the intensity of the rhodomain B. But if you heat it up and the intensity get down, this is in case of conventional heating. But in case of microwave heating, the 1 watt is enough to decrease the intensity of the fluorescence. So we can say that the fluorescence thermometer is very effective under the microwave. And we normalize the intensity, and we see that there is a difference between the continuous phase and the dispersed phase is around 20 degrees Celsius. So now we have used this phenomena to the enzymatic reactions. So we have used 2 kinds of enzyme. One is glucose oxidase, which is a low temperature enzyme, and another is glucose isomerase, which is a high temperature enzyme. First, the enzyme is mixed with water and a reactant, and then we put it, we make the emulsion. So when the emulsion, every droplet contains the whole working solution and the reactant. And after the reaction, we will get the product. We have used 1 to 510 watt microwave for both cases, both enzymes. And this is the result for microwave irradiation to the glucose oxidase enzymatic reaction is the low temperature enzyme. Here first we start from the conventional heating, and we see the reaction conversion is around above 80, 86, 87, and if you put in the long time, I mean 120 minutes, then it decreases a little bit. And if we heat it up with microwave heating only for 2 hours, we will get 84.93% of conversion. That means there is no significant differences. On the other hand, in immersion system, we will get the same results from conventional heating. But under microwave heating, if we irradiate more power, then we will see the conversion rate is decreased, and if we use 10 watt for only 4 minutes, there is almost no reaction. That means enzyme can be deactivated under microwave heating if we use high power. So it can be happen due to the protein of the enzyme get denatured or yes, denatured. So we have used a high temperature enzyme also. This is the microwave irradiation to the glucose isomerase enzymatic reaction. The optimum temperature of glucose isomerase is around 60 to 70 degree, whereas the glucose oxidase was 30 to 40 degrees Celsius. And for conventional heating of glucose homogeneous system, we'll see the around 50% of the yield we get at 60 minutes. But in microwave heating, we will get 30 minutes, similar amount of yield. So that we can say that primarily the microwave needs less time to get that much energy, that much yield. So we have summarized here our present work that dispersal phase selective heating of WO immersions by microwaves. Our objective was analysis of microwave-induced local temperature of WO immersions using fluorescent molecular thermometer, and the application of the enzymatic reaction to the microreactor. And we found first that we evaluate the microwave absorption characteristics and microwave heating characteristics of the immersion, and we analyze the local heat of the immersion system, and we found that 20 degree difference between the dispersion phase and the continuous phase. And finally, we have shown the microwave application, the microreactor, that low enzymatic optimum temperature reaction, the enzyme denatured at high power, whereas in case of high temperature enzymatic reactions, the local heat generation occurs due to the selective heating that can regulate the enzymatic performance. Finally, we can say that the WO immersion has a specific microwave heating behavior due to the selective heating of the dispersed space. Here is water, and it will be influential for the development of an emulsion-based food using microwave heating, and it will promote enzymatic reactions efficiently. So we have said our future work, that means our work is not finalized yet, so we will do conventional heating and microwave heating characteristics of glucose isomerase immersion system, and we will do comparison study about homogeneous system and the immersion system, like activation energy, expansion factors, reaction rate, etc. And finally, we will try to get the structural evaluation of the immersion by microwaves in situ SACS analysis. Thank you for your attention.